What is up, happy people? This is Mr. Sawyer, and today we're going to talk about spanning trees. If you look at both of these terms, you'll see there are things that we haven't necessarily discussed as of yet. So we want to make sure that we have a purpose about what it means for something when we talk about a tree, and then also what does it mean when we say we have a spanning tree. So both of these terms are going to be important in themselves, what a tree is itself, and then also what a spanning tree is. So let's keep that in mind as we go through today's lesson. Our central question, we want to talk about Kruskal's algorithm as well as Prim's algorithm, and we're going to use those to find the minimum spanning tree of a graph. And this is also coming from the Standard Course of Study 1.02. Now, before we go on, I want to go back and talk about Dijkstra's algorithm, which we used in order to find the length or the distance, how long it takes for us to travel from a specified vertex to another vertex. And so, excuse me, again, we're seeking a way to travel from a single point to every other point. And as a result, we create a spanning tree. And while we're looking at that, let's look at an example of us utilizing Dijkstra's algorithm. This particular question, we've gone over this once before, but we want to talk about finding the shortest path from A to I. And in order to do that, what we said we needed to do was to take each of our points here, and because we're starting with A, we're going to put a 0 at A, and then for all the rest of our points, we're going to put an infinity. All right, and basically what we're going to do as we go through, and we're going to visit each vertex, we're going to change the values that appear for each vertex, and in doing that, that'll allow for us to determine what is the shortest route that will get me, in this case, from point A to point I. All right, so we're also going to create a list of what we call visited vertices. So I'm going to put a little text box right here. It's going to say, I hope it types visited vertices. All right, and obviously because we started with vertex A, we're going to put that on the list first. So then from A, what we need to do is we need to calculate distances to the adjacent vertices from A. So if we go from A to B, that distance or that distance then turns into 5. Let me change the color right quick. That changes to 5. All right. At C, it changes to 9. And then at D, it changes to 8. All right, now that's all we're going to do right now. And then when we look at that, we're going to say, okay, now looking at this set of vertices, the question is, okay, what's the next one that we can visit? And the way that we determine which one we visit next is by finding the one that has the lowest value, and in this case is vertex B. So we're going to visit B next, and where we get to B is from A. So we're going to also shade this particular segment from A to B. All right, and put B on our set of visited vertices. Now, the same thing that we did with A, we're going to do with B. We're going to look at adjacent vertices. So if we go from B to E, we're going to take 5 plus 11 and get 16. Likewise, going from B to C, we do 5 plus 3 and we get 8. Because 8 is lower than 9, we're going to replace that 9 with the 8. All right, now we finished with B. We can mark that off, and we say, okay, where do we go next? Somebody says, well, we have a couple of choices. We have a couple of 8s, so we can visit those in whatever order. If you want to go to C next, okay, we can go to C next, and the way we get there is traveling from B to C. We're going to do the same thing from C. We could do 8. From C to E will be 18, but because that's bigger than 16, we're not going to keep it. From C to F, that will be 15, so we do want to keep that right there. So we visited C. We're going to visit D next, and the reason why we visit D next is because, again, it has the lowest vertex value of 8. So we visit D and we get there by way of A. Alright, so we're going to draw a line here going to D, and then if we go from D to F, that gives us 12. Alright, don't forget, if you need to take the time and pause this, please feel free to do so. Alright, so we're finished with D, and then we look for the next lowest point, which in this case will be F because it has 12. Alright, so we go from D to F because it had 12, and then if we go from F to G, 12 plus 9 will give us, I can't do my math right now, 12 plus 9 will give us 21. Alright, we're looking for the next lowest vertex, and that will go back to vertex E with 15. In order to make, with 16, in order to get that 16, we came from B to E. We got 16 at E going to G. That'll be 22, but because it's lower, we're not going to keep that. We will visit G next. All right, and we get there by way of F. All right, and then that 21 plus 5 gives us 26. I'm going a little quicker right now. Also, 21 plus 8 gives us 29. So if we look and see what we have next, we have that we go to H next. Go to point H. All right, and then if we do 26 plus 4, that gives us 30. So the way we'll get to I is by way of G. My line's a little crooked. I'm trying to draw with a mouse. All right, so we have that our shortest path from A to I is 29. But also what we notice about this particular graph is that we also have the shortest route to any of the other points if we happen to start at point A. And if you notice the shaded graph that we have right now, a couple of things. We have included every single vertex on this particular graph, but also what we have done is we have created what is called a tree, because if you look at the purple graph that has been created right now, there are absolutely no cycles on this particular graph. There are no ways that we can create any loops or anything like that. So as in to go from one point directly back to another without having to go back over a repeated segment. So what we have here is what's called a spanning tree. All right, and a spanning tree, again, as we're going to see in a few minutes, what it would do for us is that it will cover each point. Okay, it's going to be a connected tree, a connected graph without any cycles that covers each point. So let's go back to this PowerPoint and let's run through this right quick. Real quick, right quick. Let me clear the screen. Sweet. So again, the question was, if I can get this, here we go. What is a tree in terms of graph theory? All right, and I gave you some insight as to what a tree is. We got a little happy tree right here because trees make us happy. Awkward silence. All right, so what is a tree? A tree, again, is a connected graph that does not contain a cycle. A couple of properties of trees. A tree has n vertices and n minus 1 edges. Trees are used in many different places, such as ancestry charts, chemical diagrams. I should have put an S on that, and to help calculate probabilities. All right. And if you look in your book in section 5 point, I believe it's section 5.4, we begin talking about trees and their properties. So if you want to look at that as a resource, and also when we get to looking at the assignment for this evening, we're going to come from there as well. So yeah. All right, an example of a tree. I'm gonna draw this on the side right here. I hope it do right. So if we got a line here, all right, put another line right here. Okay, let's try this again. Right here, right here, right here. Okay, let's try this again. I'm trying this new software, and I'm hoping I'm doing all right, but I guess I still got some learning to do. All right. So if you notice in this entire graph, and I've kind of made this a rooted tree, as in I've given it a specific root to start with, and we're going to discuss that more on tomorrow. All right, but right now, if you notice one thing about this tree, it has no there are no cycles in this particular tree, and I apologize that I keep starting that. Now, an example of something that's not a tree. If I was to put another edge, click and click, psych. Wow, this is definitely not smart, boy. I thought I had it, but it's okay. We're gonna make it work. If I put another line right here, now I don't have a tree because if you notice those three segments, we have now created a cycle, so that would not be a tree. All right, but without that, then yes, we would have undo a tree. Awesome. Now let's talk about what a spanning tree is. If you're given a specific graph, a spanning tree is a subgraph that contains each point of the graph itself. And we said that one of the main keys in discrete mathematics is to talk about optimization. So when we talk about the minimum spanning tree, which will also be referred to as the MST, we're talking about the spanning tree, which means we're going to touch each point. It's going to be a tree, which means we're going to have no cycles. All right, and we also talking about being minimal, which means it'll have the lowest weight. All right. So let's see. We have a couple of different methods that we can use in order to identify the minimum spanning tree, and the one I want to spend the most time looking at is what we call Kruskal's algorithm, and I'm guessing it's named after this guy named Kruskal. All right, and it's a few rules here. We want to find the edge with the lowest weight. We want to continue finding edges with the lowest weight unless the edge that we select will create a cycle in the entire graph. And then what we're going to do is we're going to continue until all the points have been included in the tree in the particular subgraph. All right. So with that, I have created, drum roll, we have created a GeoGebra tool that will do that for us if I can get it to switch tabs, which is not doing. So if I hit Control 5, here we go. And let's clear that off right there. So we're good. If you notice, we have this particular graph here, and there's a lot of stuff going on here. We see we have a lot of edges that are connected. We have a lot of, again, just stuff going on. And what Kruskal's algorithm, let me hide that sidebar right there. Let's see if I can hide that. Let me move that out of the way. Let's go back to the, I don't want to write on the screen right now. Let's take that off so I can move that out of the way. There we go. All right, let's move that out of the way so we can just deal with the graph itself. Awesome. So what Kruskal's algorithm says for us is that we want to start off by observing this graph and finding the edge that has the lowest weight. In this case, we're looking at all of these lengths of the sides, which could represent, again, physical lengths that could represent costs and different things like that. But what we want to look for is the edge with the lowest weight. And so I'm thinking, okay, looking at this, the lowest weight that we have thus far is the one that is 15. So we want to select that, and I'm gonna make that a little bit thicker. Let's see, let's make that thicker. Okay, let's turn that off and let's clear that. Let's clear that. Let's go back and turn that back off. So turn that off, and let's, so we got this line right here that's gonna be part of it. All right. So then the next thing we do is say, okay, hey, let's look for the next lowest length, and if, as long as it doesn't create a cycle, we can include it as part of our subgraph. So y'all saying, oh, Mr. Sawyer, it's the 17. And if you said 17, you would definitely be correct. So the 17 will be the next part. All right. And then we just continue this process, find the lowest segments as long as we don't get a cycle. So you say, okay, well, let's look at the 18. We got the 18 right here. We're going to include that as part of it. The next one is 19. So we have 19. And again, if you need to slow this down, then we can slow it down. That is no problem. So then the question is, the next lowest edge that we have is 20. However, if we look at this 20, I want to pay special attention. If we look at this 20 and we were to try to include that, you notice that it would give us a cycle. So we cannot include this as part of our subgraph, which will create our minimum spanning tree. So while we know that 20 is the next lowest number, we will have to skip it because of that particular reason. And so then continuing on, we see that the next lowest number we have is 22. So we include that as part of it. And now we have a pair of 23s. We have a pair of 23s, but then someone says, well, Mr. Sawyer, it really doesn't matter for a couple of reasons. First of all, either of these segments will result in a cycle. And second of all, at this point, we already have each point that has been connected by a tree. So then to find the length of this minimum spanning tree, we simply add up the lengths of the selected edges that we have. That's 19 plus 15 plus 18 plus 17 plus 22. That's 40, 59, 69, 79, 89. I believe 91 should be the final answer that we get. 9 and 8, 7, 7 and 9 and 6, 6 and 5. So there should be a total length of 91 for the minimum spanning tree. And again, that comes from adding up 19, 15, 12, 17, and 18. Once again, that's Kruskal's algorithm. What we did is we started with the lowest edge that we have, and we continue adding edges to the graph as long as they do not create a cycle. All right, let's go back to this. So we should continue until we have all the edges included in the tree. Now, there is another algorithm that's sometimes used, and I'm going to type a little bit right here. It's called Prim's algorithm, and it's a little bit different. Now, let's back up. Kruskal's algorithm will guarantee that we get the lowest minimum spanning tree. Prim's algorithm, while it gives us something that works, does not always guarantee that we get the minimum spanning tree. And the way that Prim's algorithm works is very similar to Kruskal's algorithm, in that we start with the lowest weight. But what we do is we find the next edge, which is attached to one of the edges that we've already used. So step 2 changes. So find next lowest edge, and I'm gonna put this in caps. Attached to a used segment. All right. Unless the edge creates a cycle, and then we're going to continue until all points have been included in the tree. So let's go back to our diagram. If you need to pause the video right here in order to make sure that this slide is recorded, take a couple of minutes and write this down. Once again, write it down. If you need it, write it down. Awesome. Now let's go back to this graph. I want to put these, I want to change these back up like the way they was, so that we can look and see if something different happens this time when we consider Prim's algorithm. All right. And I'm hoping everybody says, well, Mr. Sawyer, yes, we're going to still start with the same segment that we had before, which was segment 15. All right, and I agree with you. That's what we're going to begin with. We're going to start with that one right there. Now, what Prim's algorithm says is, hey, we have these 2 points right here. Let me see if I can put some labels on these points. Let's see. Let's show the labels right here. So we got point D and point E. All right, let me bring these points back in. I'm just going to bring these point labels back in. All right, so we can call these out, and we can see what's what. I believe that's what C, and I think that's everything. Cool. So now, to find the next point, we want to look for the next lowest segment. However, for Prim's algorithm, it's the next lowest segment attached to what we already have. So either from D or from E, what is the next lowest edge that we have? And I'm hoping we said, hey, it's going to be DF. If you said DF, you would be correct. All right. So now we still have some unused edges. We're looking at either from D or from E or from F. What is the next lowest segment that we have? And in this case, it will be from F to A. So we include that as well. And then either from C, from A, F, E, or D, what's the next lowest segment that we have? And I'm hoping we would say yes again. It will be 19 in this case. It'll be 19. All right. It'll be 19. And then again, we're looking at the corners that haven't been used at this particular point, C, E, A, F. And we're looking for the next lowest segment, which will again be 22. So we do happen to get the same segment in this particular, the same minimal spanning tree in this particular case. But Prim's algorithm does not always guarantee that we get the same thing. But in this case, we happen to get the same graph. All right, so what we have talked about today, we have discussed what trees are, and we have talked about minimum spanning trees. If you need to look at this lesson again, please do that. Otherwise, what I need for us to do is to look at the assignment on page. All right, and I'm going to type this in so that there's no excuses for our assignment for today. All right, if we go to Control M, I'm gonna hit Control M. I got a new page, and it's gonna be a homework. All right. There's going to be two parts to that. First part, page 258. 258. Numbers. One through 5. And then also and then we're going to have a second page. We're going to go to page 268. Page 268. And we're going to look at numbers. One through 6, and then we're going to also look at, we're going to use Kruskal's algorithm in order to complete problems 11 through 16. Once again, if there's any questions, comments, or concerns about what we've done today, please send me an email and I will try my best to get with you as soon as possible. I think that's all I have to say for right now. We're going to do this thing again on tomorrow. You all take care. Also, before we go, just a heads up, you will have a test on Thursday when you go to the computer lab. There will be a test, and it will include minimum spanning trees, and it will include what we call binary operations, which we will discuss on tomorrow. All right, tree traversals, binary operations. So if you want to read ahead to section 5.6, so that when you see your lesson on tomorrow, you'll have a little bit of idea what's going on, that would be great. Otherwise, I guess that's it. I will talk with you all again tomorrow. Take care. Peace.